frameworks and how their performance and memory requirements are different. This presentation is based on the following paper. So actually, as you know, PyTorch and TensorFlow, they are the most common. So here we have taken slightly older version of Torch. Okay, the main point of presenting this is also to show the characteristics of each of these types of convolutions. Right? We have yesterday discussed direct convolution, GAN-based convolution, and FFT-based convolution. We also discussed Vinograd-based convolution, but I'm not aware of any framework which uses exclusively Vinograd, because as I said, Vinograd is not universal. So if you there are some frameworks which use Vinograd, but not exclusively. That means they will be using Vinograd along with GAN. Okay. So here different frameworks use different strategy for doing convolution. Okay. So before we go on, one more point is that you don't have to memorize this paper. Okay. So don't think that you are not understanding. I mean, or this is like this is like a exploratory study, a comparative study. Okay, so they may be presenting a lot of results, not everything you have to memorize, but just try to understand what are the constraints or what are the differences. So we will not expect you to memorize the results of this, but try to understand what are the characteristics of direct GAM and FFT-based convolution. So these two frameworks, they use direct convolution. CAF, Torch, Kuhn, NN, and Theano, 2DNN. TensorFlow, they use GAN-based convolution. FP refers to Facebook. Okay, Facebook's FFT and Theano 50, they use FFT-based convolution. Okay, so we will compare them. So now of these 7 frameworks are selected for evaluation: CAF, 2DNN, FP50, Theano, Torch 1, CUDA, COM2, and this Theano for M. So first of all, conv layers take the largest fraction of execution time. That's why they have studied conv layer. So as you can see here, this is conv layer. This all is conv layer. This all is conv layer. This all is conv layer. So that's why they have chosen only convolution layer. Other layers like ReLU, pooling, FC, concatenation, they do not take large amount of execution time. That's why they have chosen these. They have chosen convolution layers for study. Okay, now one by one we will compare different parameters. So they change 5 parameters one at a time. So I explained stride yesterday, I mean, in a very brief manner. I hope you would have already understood it, or you could study from online. That's a very simple point. Then kernel size is the filter size, right? For example, we have this. Kernel size is here. Kernel size could be like 3 cross 3, 5 cross 5, 7 cross 7, and so on. Okay. Now, image dimension. I hope you know what is image dimension. So, an image could be, for example, 224 cross 224 or 50 cross 50, whatever. So they have actually. Usually the image size is 224 cross 224. But it could be different also, like 227 cross 227 or 299 cross 299. So they have checked it with different input size. Mini batch size is the, it's like it is the batching size. It is the how much batching you do. You're doing. Okay, I've discussed what is batching, so that is same as mini batch size. And filter number is how many filters are you using. Okay. Each layer can use more than one filter, right? Because in each layer you are finding out multiple properties. For example, if you want to detect a human, you will have one filter which tries to detect the face, one filter for hand, legs, stomach, and so on. So depending on that, you could have a lot of filters. So here you can see they have changed the filter.
So what is the difference between kernel and filter?
Actually, in one blog I've written that kernel filter are different, but as far as I think, for most of our purposes, kernel is same as filter. There is, I think, some minor difference. I will try to look it up, but for us, sometimes they use the word filter kernel, so it is same actually. Filter size. The size of
Okay,
each
sir.
filter. Size of each filter. I'll try to look it up again. What is the minute difference? But uh, for most of our purposes, kernel filter they are same. Okay. So let us see the results one by one. So let us see FBFFT. Okay. So here you can see first thing is it works only for stride size of 1. It doesn't work for stride greater than 1. So that is one limitation of FFT. As I said, FFT is not a universal solution. Now, one good thing is this FFT has very low runtime. It has the almost least runtime. Okay. So that is the greatest advantage of FFT-based convolution, that it is fast. And even TNFFT is not as good as FPFFT, but still, like for example, here again it has least execution time. Here, right, it is low execution time. Here it is very high execution time. Here also it's high execution time. Here also high execution time. But here TNFFT, although it is FFT based, but it is not as good as FPFFT, but still it is sometimes it's good. Okay, CAF. CAF is the dark green. So dark green is neither. I mean, it is not as good as FPFFT, but after FFT based, it is it's good. I mean, it's not especially poor. It is like here it is on the higher side, but here also it is somewhat. Here actually you could hardly distinguish this and this. Here also it's not dominant. It is not much difference. Here also it's not very clear where it is, and so I mean usually it's very like here because runtimes are almost similar for other frameworks, so it's difficult to distinguish between them, and even these runtimes are not much different from each other. They're almost same, but we can just see the highest runtime. We can see the lowest runtime. So that's why I mentioned FPFFT and Theano one, but others are not so easy to distinguish. So in terms of performance, FPFFT is best, cuDNN is second best. Let us see cuDNN is second best. How cuDNN? So this one, the orange cuDNN. So here it is the second best. Most of the figures it is not visible, right? Only in one figure it is clearly visible. Other figures it is behind, but you can see that it is the second best. Here also it is second best. Here also second best. Here also, I mean, here this is second best, but it is after this. This is this, and this TNFFT is the worst. I mean, only in this figure it is second best, but in all other figure it is worst. Here I don't see that. Probably it is behind this. TNFFT is probably behind it. So FFT-based convolution is more efficient than other types of convolution. For small kernel sizes, cuDNN is faster than FPFFT. So, can anybody tell me the reason why this is so? Yesterday we discussed. What is the biggest problem of FFT? One was that it doesn't work for stride greater than 1. What is the biggest limitation of FFT? So one of the limitation was temporary memory requirement is huge. But why? So I've given you some hints. Why does it require huge amount of temporary memory? And one more thing is, instead of matrix multiplication, here we do element-wise multiplication. So I've given you so many hints.
So we have to consider the same size of the image and the kernel, and we have to do the padding.
Yes, very correct. Yeah, we have to pad the kernel to be of the same dimension as the input, right? So if your input is 224 cross 224, but your kernel is only 3 cross 3, then you have to pad the 3 cross 3 kernel to 224 cross 224. So you can just imagine how much extra pixels you have to add, and that causes, because of that, you have to use a lot of temporary memory, right? So operating on that will be additional overhead. Very nice. So that's why for small kernel sizes, FFT-based convolution is not good, but for large kernel sizes, it is good. CUDA Cornet 2 works well only when the mini batch size is a multiple of 128. Actually, that is not visible from here. Here, mini best size. Here means mini best size. So, okay, here, yeah, this purple one. It goes up, goes down, goes up and down. It goes up and down. So only when this multiple of 128 it works well. Yeah, among GAM-based convolution, 2DNA provides the highest performance. So as I said, 2DNA is the second best, and it is also better than other. 2DNA provides the highest performance. So one conclusion which we will arrive later on, but I'm telling you in advance is that 2DNA is the overall best. Okay, 2DNA is the overall best. So keep that in mind. So 2DNA provides highest performance, except that for when filter number goes above 160, Cyano core M1 provides slightly better performance than 2DNA. So actually, this Cyano, I don't think it is even popular nowadays. So popular ones are TensorFlow, 2DNN, and PyTorch. So I think this is somewhat older version of Cyano. So that's why where it works well is not so interesting to us. For us, more interesting is FBFFT. I think now they made it public. Previously, I think Facebook developed it. I think they have made it public. I don't know how much development is happening in FBFFT. But Tensor, so I think TensorFlow they have not selected. So here there is no TensorFlow, right? I mentioned the TensorFlow here, but TensorFlow they have not selected for evaluation. So you can consider this more as a research study, not so much like a practical study. Okay, CUDN provides highest performance, except that for filter number above 160, Cyano core M1 provides slightly better performance than CUDN. Now, do these frameworks have any restrictions? One restriction I already mentioned. Can somebody repeat it? That means it is applicable in some cases, not applicable in other cases. What is the restriction of FBFFT?
You need large memory.
Memory.
Anubhav, what are you saying?
Some memory requirement.
No. Restriction means it can't work at all. I mean, whether it works slowly or quickly, that is a separate question. But by restriction, I mean that you can't use it at all.
For small size kernels.
That's it. Anupam, that's it.
For small size kernels,
Small size kernel, it is inefficient, but at least it works. I'm saying restriction. By restriction, I mean it can't work at all.
For stride greater than 1.
Yeah, stride. Stride is the biggest problem. So here this point was FFT based one works with all the tested parameter except that stride size greater than 1 is not supported. So this is the biggest. See, these restrictions you have to take into account. If the performance is slow or fast, that is an important consideration, but that comes secondary. First of all, you have to find out whether it works or not. Now, GAM-based con works with all the tested parameters. So that is the, as I said, it's a universal solution. Okay, matrix-based convolution is a universal solution. Now, CUDA ConvNet 2, it is based on direct convolution, right? Remember that. CUDA ConvNet 2 is based on direct convolution. Here. This is based on direct convolution. Now, it supports only square input images and square kernels. Mini best size must be a multiple of 32 and filter number must be a multiple of 16. So these are additional restrictions or limitations, which is not, you have to really keep very special eye here. So CUDA ConvNet, this purple one. So certain mini best sizes and I think kernel sizes and I think here also it's not a continuous, as you can see, filter number. This is not a continuous graph. Only for certain filter numbers it works. So that's what mentioned. The filter number must be a multiple of 16. So these are certain limitations. I don't exactly know why this kind of limitations they have imposed in this framework. Okay, now let us see which functions take the largest amount of time. So see, this is a very good paper on profiling. If suppose you join a company, they ask you to take the existing product and try to optimize this. The first thing you have to do is profiling. So the first thing they have done in profiling is this one, this part. First profiling you do, okay, let me focus on pod. Let me not waste my time with FC, ReLU, cooling, because that is not so important. This is how architect's mind works. Where is the bottleneck? So, which is the, where should I focus my efforts? Then, so now here again, you will see which functions take the longest amount of time. So in CAP, GAM is the most time consuming. Now, IM2Call is a very well-known, function which achieves lowering. Right? Yesterday I discussed lowering, where you take a convolution, you lower it into a matrix multiplication. You remember that, right? So that to achieve that, there is a function called IM2Call, and opposite of it is call to IM. So image to column, convert this image into a column-based, multiple columns, so that you can do matrix multiplication. So that is this IM2Call. So here, all of these are GAM-based convolutions. So here, GAM operation takes the largest time, and unrolling is this IM2Call and call to IM. They take the second largest time. Okay, so here it is. Now, one more thing you can see this Kudian, and it also uses Vinograd. So that is another interesting point. So here, this part is Vinograd. So as I said, there are frameworks which use Vinograd, but only for certain, sizes of input image and filter size. Vinograd is not a universal solution. So I guess this WGrad is Vinograd. Now, how it uses is I'm not for which sizes it uses. I'm not very clear, but it does use it. So actually, Kudian can select from multiple types of algorithms: GAN, Vinograd, FFT, and so on. I think direct convolution is also possible. So out of the multiple possible solutions, it will select the one which is best for each case. Now comes Theano FFT. So now these two are based on FFT. So Theano FFT, majority of the time is spent in preparing and transferring data between CPU and GPU. So you remember heterogeneous computing we discussed when I discussed about GPU. So in GPU there is a host which is CPU, and there is a device or accelerator which is GPU. So CPU prepares the data, sends it to GPU, and GPU does the computation, sends the data back to CPU. So as you can see in Theano FFT, this copy operations, CUDA mem copy, that takes a lot of time. And K_copy, I don't exactly know. I think this is also for host to device copy, but I'm not sure. CUDA mem copy, I'm sure, and CUDA K_copy, I think. Going by this text, I think it should be for device to host copy. Now, FB/FFT, here also, there is decimate in frequency, then there is transpose. So transpose operation is required in FFT-based convolution, and still there is some amount of GAM also. Matrix multiplication is also happening. So I guess they also use GAM for special operations. That means whenever FFT is not possible, that time they will be using GAM. So here in direct convolution, these three, 1, 2, and 3, these three functions take a lot of time, and they have not fully explained what these functions are. So this is the type of function names you get from the profiling tools. Okay. Sometime I will try to show you the profiling tools, the results of profiling tool, just to give you an idea how do we do profiling. So what these functions are, they have not explained, but these are the functions which take the longest amount of time. Okay, now let us see memory consumption. That is very, very interesting, very, very important. So direct convolution takes least amount of memory, GAM takes somewhat higher, and FFT takes really highest amount of memory. So here you can see for even when stride is what, FFT takes so much extra memory, right? Almost more than 1300 megabytes. That means little bit more than 1 gigabyte, right? 1.2 gigabyte, right? 1.2 gigabyte. 1.2 gigabyte. Now here, now FD50, you can see this. This has highest memory consumption for all cases. Has highest memory consumption. I mean, of course, in one case, this Theano FFT, which is also based on FFT, that has sometimes becomes extremely huge memory consumption. So here you can see 6,000 megabytes. That means almost 6 gigabytes. And here it goes 7.5 gigabytes. Just a small convolution. Suppose you have a P100 GPU which has 12 gigabyte global memory. It will take 7.5 gigabyte will just go in one convolution. So that is infeasible, right? So that means it's not a good framework. And direct convolution, this Torch, QNN, and CUDA Core 2, right? This purple one. This has almost the least. This is the least amount of memory consumption. Torch QNN is also has low consumption. Then in between comes GAN based. So among GAN based, Torch QNN takes least memory. For large kernels, QNN takes least memory. Now, but Theano FFT generally takes less memory than FP50. But for certain configurations, Theano FFT takes huge amount of memory. That is here in this figure. You can see the kernel size figure. Here it takes huge amount of memory. For others, it doesn't take as much memory as FP50. Here it takes less, but in some cases, it takes huge amount of memory for certain configurations. So now the result is CUDA Core 2 is best for platforms with small memory because it uses direct convolution. So that means whenever you are constrained by memory, you should use CUDA Core 2. And as I said before, cuDNN is the best platform if you consider multiple factors such as performance, memory consumption, and versatility. That means it has no restriction. It works for all possible configurations. Right? Memory consumption is not very high. Performance is reasonably good, although not as good as FP50. But if you consider multiple factors, then cuDNN is the best. Okay. And any questions till now? Okay.
Sir, why FBFFT consumes a lot of memory for its stride of 1? Why?
No. So for any, so I think for stride of 1, right? They must have set some other kernel size. They must have set probably a small kernel size. So I will have to. I think there is some. Let me see that I have that paper for now. Just let me open that. So see if their default configuration when they are changing the what you call kernel size, they are keeping. Sorry, you're asking about here. Right? So when they have a stride of 1, they must have set certain kernel size. So if that kernel size is small, then that means a lot of memory consumption will happen. So I'm trying to open that paper. What is the default kernel size? Okay, so based. Yeah, okay. Here 5 group of stride is S. So just 64.28. B is the batch size. Meaning the size input image size is I. Filter kernel size is K. The second last is K. Kernel size is 11. So okay, so this stride figure, kernel size is 11 cross 11. All right, so kernel size is 11 cross 7. So and the image size is what? Image size is 128 cross 128. So now you can see the kernel size is just 11 cross 11, and the image size is 128 cross 128. So you have to pad your 11 cross 11 kernel into 128 cross 128 size, metric size. So that because of that
it is related to the stride.
No. See, I mean, how it is related to the stride. See here, No, you have to see the scale of other figures. See here, what is the value? More than 1300, right? And here also it is more than 1300. You are not looking at the scale. Here, initially it is less than 1000, but right after this, so here, so see 128, right? Input size is when input size is 128, and so here also you can see it is around 1500. It's not here. It looks very high to you because the scale is different. Is it fine? Who has the question?
Yes, sir.
Others in other figures, scale is just it has been compressed, but it doesn't mean there it is less. Here you see it is more than 10,000 megabyte. That means more than 10 gigabyte. So it's high for all the cases, not just for stride 1. I mean, in all these figures, stride is already 1. In all these figures, stride, by default, stride is 1.
So what is this filter number and C and D? Is there any difference in kernel size and filter number?
No. Yeah, filter number is how many filters are there. Let me. Filter number. So filter number is how many filters are there. I think I will show you. Let me open some. I have some L6b, which was the PPT that yesterday's PPT. Just show you. This is input features. I will try to. This is the input. These are the channels. I will show you actually a typical, a typical LXNet or some CNN, and I will show you what is the number of filters in each layer. Each layer uses multiple filters, not just one filter. So that is the filter number. Okay, I will write it down. I will send you a typical neural network configuration which has more than one filter. As I said, you need multiple filters to detect all the features. So you will have one 3x3 filter which will have some shape. You will have another 3x3 or 5x5 filter which will try to detect another shape. Okay. So I will answer this question.
Will the filter be always in a square metric or it can be in rectangular too?
Filter need not be square.
And kernel should be
so
always
sorry. Yeah, filter number need not be power of 2 or anything. It could be like any number. It could be any number. And kernel sizes are usually odd cross odd. There is a reason for this actually. Why don't we use 4x4? Why do we use 3x3, 5x5, 7x7, 11x11? Why you generally use odd? Why not even? There is a reason for it.
Okay.
I don't remember that reason. I will, I have that in my inbox somewhere. I have it, but I will. If I look it up, I will. If I'm able to find it, I will share with you. So yeah, kernel size need not be. I mean, kernel size also need not be square. There is also like there are also filters like 1x3, 3x1, 3x3, and so on. So and 1x1. So all those filters are possible. Even these filters are possible. I think MobileNet uses it, or some of the very popular networks they use it. It need not be square.
Okay, sir.
Any other question? Okay. So this was summary till now. Now let us try to do microarchitecture. That means go somewhat more deeper. So all these experiments have been done on GPU. We have already discussed with you what is GPU architecture in a brief manner. So now let us see some more metrics on GPU. So achieved occupancy is one metric which shows the ratio of average active warps per active cycle to the maximum number of warps supported on the streaming multiprocessor. So each streaming multiprocessor can support, suppose every warp can support 1,000. Sorry, every streaming multiprocessor, suppose it can support 1,000 warps. Right. So now out of the 1,000 VARPs that can run. Now, suppose for a particular application only runs 20 VARPs because of the thread, because of the branch divergence. I discussed what is branch divergence, I guess, yesterday. So branch divergence means how many VARPs are actually active. That means whether there's if there is huge branch divergence, then average active VARPs will reduce. But if there is no branch divergence, then all the VARPs are active. Okay, so that's the idea. And VARP execution efficiency is ratio of average active threads per VARP to the maximum number of threads per VARP. So maximum number of threads per VARP is 32. Okay, so out of the 32 VARPs, how many? That means in each VARP, how many threads are active? Right. Example: some of the threads may remain idle; they may not do any work. If you don't have sufficient parallelism, right, or if they are stalling for memory accesses, then those threads will remain inactive. So average active threads per VARP is the suppose out of 32, only 10 threads are active in general on average. Other threads are they are not active because there is not sufficient parallelism. GPU is all about massive parallelism, but if there is not sufficient parallelism or if there is branch divergence, then many threads will remain inactive. Okay, so that VARP execution, that means execution efficiency of each VARP, and here how many VARPs are active, okay, and how many cycles we are actually doing work. Sometimes we are just transferring the data to CPU, then GPU is not doing anything. So we don't. That is not called an active cycle. That means the VARP execution has to happen. So here is the usage of registers. How many registers each framework is using? I mean each thread register usage per thread and shared memory usage per block. Okay, so these two factors are related. Okay, so for example, suppose if you have to go to local memory or global memory, right? If you're not using sufficient registers, you have to go to local memory or global memory. So we should use sufficient number of registers. But if you try to use too many registers, okay, suppose there are only there are 1,000 registers. Registers are limited, right? And now each thread uses suppose 100 registers per thread. Now how many threads maximum we can run? Tell me. How many maximum number of threads can we run?
10.
We can only run 10 threads. We can only run 10 threads. That means now parallelism will be limited. Right? We can't run a lot of threads because each thread needs so many registers. So your number of maximum number of threads that you can run will be very limited. Right? So that's why this number should be neither too high nor too low. Okay, so you need to balance. Similarly, now let us see shared memory. So suppose a GPU has only 48 KB of shared memory. Right? Now this is the here. So for each now each block is using suppose 16, right? 16 KB of shared memory. So how many blocks can run? Only 3 blocks can run. Okay. So if each block is using too much shared memory, then only few blocks can run. But if each block uses very little shared memory, then it has to go all the time to global memory. Right? That is also not good. So that's why there is always a trade-off. Our whole life is about a trade-off. You can't just push on one extreme or other extreme. You have to really find a right balance. If you're using too much shared memory, then your parallelism is limited because only few blocks can run in parallel. But if you're using very little shared memory, then you have to always go to global memory. So so this thing we have shown. Now let us analyze somewhat more. Now, CUDA coordinate 2 has the least occupancy on GPU. Why? Because each thread uses many registers. How? CUDA coordinate 2. Here, it uses so many registers, as I said. So here, because it uses so many registers, now we can run only few threads. Only few threads can run at a time. So memory latency cannot be effectively hidden. So now let us see this example. Now, Tesla GPU has this many registers per streaming multiprocessor. They have actually used Tesla K40C GPU. Now, each thread of CUDA coordinate 2 uses 116 registers. So, how many threads can run? You can do this math. 564 into 116 is this, which is just below this. Which is just below this number. If you were to make instead of 564, if you were to make it 565, that will be above this number. Right? Also, you have to make sure that number of parts multiplied by 32. So this number should be multiple of 32. Okay, number of threads, because threads always run at the granularity of a bar, and each bar has 32 threads. So effectively only 17 bars will run, right? So how much is this number? 32 into 17. So this is 554, isn't it? Okay, so this is the 544. So although 564 threads can be active, but because we will always run at the granularity of bar, so effectively even 564 threads cannot run. Only 17 bars will run. Right? So is it clear, or was I confusing? Let me discuss again. Okay. So see, we have this many registers. Okay, we have this many registers. So and each thread needs 116 registers. Okay, so let us do the math. We'll take the floor. Let me do the calculation, exact calculation, and then we'll do the rounding off. 65536 divided by 160. So the number I get is, if I divide 65536 divided by 160, I get 564.96. Okay, so we will always have to take the floor. So I took the floor as 564. Now you have to again find out if these are the number of threads, then how many bars can run. So I find out 564 divided by 32. So I do 564 divided by 32. So this is 17.662. Okay. So again, we have to take the floor, because a bar will run in completion. It will not run half bar. So we can only run 17 bars. So at maximum, only 17 bars can run. Now each SM can allow up to 64 active bars, out of which we are only running 17 bars only. So that's why we don't get sufficient parallelism. Okay. So how to improve CUDA coordinate 2? We have to rewrite the code so that the number of register usage is reduced. Okay. If each thread can work with less number of registers, then we can run more number of threads, more number of bars, and we can effectively hide the memory latency. So now this calculation, is it clear? Because we'll ask one numeric question based on that.
So what is the significance of WAP? I mean, why use WAP now? Why we are using WAP? I mean,
because of the parallelization. So we run. This is called actually vectorization. So multiple threads run together. They are doing the same operation. Okay. So let me show you. Actually, I should have. There is I think next presentation on this only. I thought. vectorization. Yeah, here I will share this thing with you. So yeah, can you see this? Can you see this scalar versus vector instruction?
Yes, sir.
So here, see,
Yes, sir.
when we do scalar instruction, suppose we want to do 4 additions, we have to separately issue 4 instructions. That will happen in 4 cycles. Okay, but suppose we can just issue 1 instruction, and we know that all the threads will work on the same, they need to do the same operation. So here it is, vector length is 4. In GPU, the vector, this length is 32. That's called a var. So all the threads will do the
We
same
can
operation.
change that length.
No, I mean,
We can
maximum
change
length
the
is
length.
fixed. Maximum 32 length
Why
is
so?
fixed. That you can't change. I mean, they
Why
must
so?
have actually, they must have found out. Actually, AMD uses 64 and NVIDIA uses 32. I'm sure they must have found out based on what is the optimal number. If you want to, suppose you want, instead of 32, you want to make it 32,000. Then you need to really have 32,000 threads, all of whom are doing only addition. That's very unlikely to find out. Whereas if your vector length is only 4, then you are only having 4x saving. Right? So that's the vector length can't be too large, it can't be too small. That's why I said GPU is all about massive parallelism. Unless you can find out massive parallelism, suppose your parallelism is only 8-fold, then having a warp length of 32 does not help. Because out of 32 parallel threads, only 8 threads can work in parallel. You don't have sufficient parallelism. Okay. So does that answer your question, Rachit?
Yes, sir.
Any other question? We will come to this presentation afterwards. So let us go on if you don't have any further question. Okay, so I hope this calculation is very clear to you. Given a usage of registers per thread, how to find out how many bars or threads can run. Now, let us see Theano FFT. It does not fully utilize shared memory and registers. Let us see how. So it uses very little registers. That is the other side of the problem. Because it doesn't use register, that means the code has not been written properly to actively utilize register. That's why every access you have to go to global memory. It also does not use shared memory. It uses very little shared memory. So it issues many accesses to global memory. It also has poor warp execution efficiency due to thread divergence arising from control flow instruction. That part is not shown in this table. This thing is not shown in this table, but that is just a separate observation. Okay, so that's why TNFFT has poor performance. Now, TNFFT, Theano Corvum, and Torch Tuning in CAP, they show poor global memory load efficiency due to lack of memory access coalescing. We have discussed memory access coalescing. Now, how do these frameworks have less coalescing? That is outside our purview. But we are making a statement without giving the proof because we don't know these frameworks in the detail how they've written the code. Now, among GAN-based implementation, cuDNN provides the highest shared memory efficiency because it is written directly by NVIDIA. So they know their hardware the best. That's why they optimize cuDNN for GPU, right? So that helps a lot, right? When you are designing the hardware, you also have to think about the software. This point will come again and again in this course. Although we are discussing more about probably hardware, but software is also important. So if you design hardware, most probably you will also be designing your own software so that you can extract the last bit of performance from the hardware. Now, shared memory efficiency is lowest for TNFFT due to large number of bank conflicts. So TNFFT has large number of bank conflicts, which we already discussed, and leads to a lot of performance loss. Now, GAM operations in Theano, Torch, GAP are performed by cuGlass. Again, cuGlass is also written by NVIDIA, which is optimized for shared memory. These frameworks show high shared memory efficiency. So that means if you are designing your own framework, suppose instead of PyTorch, tomorrow you are designing your own framework, you should try to use existing libraries like cuDNN or cuGlass. Instead of writing your own code, try to utilize these libraries. That will give you optimized performance. finally, last slide, overhead of data transfer between CPU and GPU. So in FPFFT, CAF, and 2DNN, this overhead is nearly zero because like as CPU is transferring the data, probably GPU already starts doing the computation. Okay, whereas in other frameworks, the overhead is large. Okay, so here, for example, this is for what? This is for Theano core M, right? This is Theano core M. Here it is, I guess, 0.65. This is almost 65%. So there is in most others, it is very, very small. So you have to look at all these overheads. So this is the, so actually, one of the biggest optimization you have to do in GPU is how to reduce the data transfer overhead between CPU and GPU. If just in transferring the data, you are taking a lot of cycles, then even though GPU is so fast, but transfer of the data happens very slowly. It's just like that. Suppose you have a factory. Factory is doing a lot of production, but you don't have efficient transportation. So your products are coming out very, very slowly, right? And that becomes a bottleneck. That's what the definition of bottleneck is, right? So that's why apart from the fact that you need to optimize, thread divergence, you need to optimize global memory efficiency, shared memory efficiency. That is focused on the GPU side. But on this interface side, CPU and GPU connection, you have to also make sure that the data transfer happens efficiently. Okay? Or while the data transfer is happening, GPU should do something else. GPU should start processing start doing the computations. Okay. And